Okay, class, now we're going to go over chi-square and recombination mapping, the other example that we'd normally do in class. And so recombination mapping is a way at looking at recombinants or unpredicted mixing of genes, and then using that information and the idea that recombination happens equally across the chromosomes to get relative position of these genes on the chromosome. Now this differs then from a physical mapping where we know, for example, in your lab course where you know the exact base pairs of where a gene lies. So let's talk briefly about linkage. So a linked allele is an allele that physically resides on the same chromosome as another allele. So in this example here, we have this one chromosome, and the PR gene and the VG gene are both physically on the same allele. And then on the other chromosome, they are also physically linked. So if we were to mate this parent with parent number 2, our possible gametes would have both the PR and the VG gene on the same allele, in this case the wild type, and then in parent 2 the mutated gene for PR and PG would both be on the same chromosome. And thus in the F1 generation, when those gametes come together, then the mutants are both on the same chromosome and the wild type are both on the same chromosome, and you get one of each. Okay, one way that we can investigate these ratios is with a dihybrid test cross. And so remember, a dihybrid test cross is where we take a heterozygous individual for 2 alleles, so dihybrid 2 alleles, and we cross it with a homozygous recessive for both alleles. And from that, because this gamete is, or this individual is making 4 different types of gametes, it's making a big Y, big R, so big Y here, big R here, a big Y, small r, so big Y, small r, a small y, big R, and then a small y, small r. The second individual, the test crosser, or the tester, is only going to contribute small y, small r, because that's the only option it has. So because of this, we have offspring that we can look at, and like the pedigree analysis, it's not always a perfect ratio, but it's very close. So we see that this is roughly 1:1 to 1:1. And so this test cross confirms the independent assortment of these alleles. Okay, so let's look up setting up this test cross. So here we have an individual that has the recessive or the wild type, or the mutant type PR. So PR, VG, VG. And then we have an individual that is got the wild type, PR plus and VG plus, and they are homozygote for those. And they create gametes that are the mutant or the recessive and the dominant or the wild type. And that comes together to create this F1 dihybrid where we have a mutant and a wild type copy of PR and a mutant and a wild type copy of VG. And to do a test cross then, we cross this heterozygote that we just made from the F1 dihybrid times a completely recessive or a tester. So this one is recessive PR, recessive PR, recessive VG, recessive VG. Now, from there, this is our setup, but we actually have to do the test to count the offspring. And so as you can see, in the PR VG offspring that we saw in this parental generation, we have a lot of those because those 2 genes are on the same chromosome. The mutant PR, VG, VG, we have a lot of those individuals because they are in the parent generation, but then we get this mixing. So we have the PR VG that are on that are opposite, right? So PR mutant VG wild type wasn't in the parental generation, so there had to be a reshuffling of those chromosomes. And the same thing for the opposite. This is actually mislabeled. This should be PR plus, and then there should be no plus here. There you go. So this one is actually the result of mixing of the alleles on chromosomes as well. So from that, we can kind of understand, just looking at these ratios, the ratios where we have the largest amount of individuals shows that they are on the same chromosome, right? Because recombination is relatively rare between genes. And so we know that because there's a lot of individuals that have PR plus and VG plus, as well as the PR, VG, the mutants, those are going to be the normal conformation. And then the mixture of these two alleles, of the PR and the VG plus, that would be only occur through recombination. So let's look at this another way. And so in our last example, we had the mutant and the wild type both coming from the same parent. But here we have the mutant and the wild type that are a mixture, right? So for the mutant VG is on one parent and the mutant PR is on the other parent. And so from this, we see that our gametes now, oops, that's a white line. Our gametes now are mutant wild type, mutant VG wild type PR, and mutant PR wild type VG. So in our dihybrid here, we have again the same mutant alleles. We have PR plus and VG plus. This plus should be up here probably. And then PR and VG, we have the same amount of each, right? So in our last example, we had one copy of the mutant, one copy of wild type for each of them. The same thing is here, but they're on different chromosomes, right? Because they were mixed between the two parents. So again, we have our dihybrid, and we do a test cross. And we see that we can count the offspring. Here, the offspring that have PRVG plus is a large portion, 965. PRVG, again, this is messed up. Let me cross that out. This should be PR. PR plus VG has 1,067, so those are our two biggest portions. So we know from that that they are on the same chromosomes, right? The smaller portions, where we have PR plus VG plus or PRVG, means that in order for those to be on the same chromosome and have a higher portion, that there had to be recombination that happened in between them. So what is this recombination that's occurring? So as you can see here, this chromosome, you can see this is in the middle of meiosis, where we're replicating chromosomes. And we have big A, big B, and big C that are normally all on the same chromosome. And we have small a, that's indicated by yellow. Small a, small b, small c are normally on the same chromosome in brown. But what can happen is we get this invasion, double strand breaks and invasion of strands that enable additional mixing of genomes. And this is good in an evolutionary context, so it increases the amount of mixture of genes so you can get individuals that are more fit to react to changes in the environment and things like that, survival of the fittest, as you know. So it's a good mixture of genes that this happens. Otherwise, if you had a mutated allele, you'd always get it if you got that chromosome. But this allows shuffling of genes. And so what we result with after these crossing over events and this recombination is now a chromosome that was originally big A, big B, big C is now big A, big B, small c. This other one was big A, big B, big C. And now it's big A, little b, big C. And the same thing we see down at the bottom here is we get shuffling of genes where this last chromosome didn't have any recombination, but its partner chromosome has been reshuffled. And this reshuffling can happen in multiple different ways, right? And so depending on who invades which strand and where the recombination happens, you can see that this, which was originally, I believe in the last slide, big A, small b, big C, because it crossed over at a different point between B and C and with a different partner, we now have big A, big B, small c, etc. So this allows a lot of shuffling to happen between these genes. Okay, so now let's look at this, kind of summarize it, right? And so if there's no crossovers, this was our original parents, right? We have, in this case, we're only looking at 2 genes here to kind of simplify things. But we have big A, big B, big A, big B, little a, little b, little a, little b. Now, with no crossing over, our products of meiosis, or of, in this case, meiotic products of mitosis, you see that there's no reshuffling, right? And they all have the parental genotype. They all look like the parents, right? In an event where there's crossing over, we see that we have reshuffling of these genes, and that the products of mitosis, so the finalized products later, we can have some individuals that have the parental genotype, we can have some individuals that have the a recombination, and we can have a mixture. So it's possible that we have both yellow and brown chromosome for all 4, or we can have, in this case, none of them. Or a third option is we have a couple, or in this case, 2 chromosomes that have been recombined, and then 2 chromosomes that have not been recombined, and 2 that have been recombined. So the top and the bottom look like the parental, as you can see here, and underneath my my camera here, and then we have 2 that are now reshuffled. So taking that information and the fact that recombination happens randomly across an entire chromosome. So I'm going to do a little drawing down here. So say we have genes A, B, and C. And I'll put little marks to where they are. Now, if we take the theory that recombination, or this breaking and recombining between partner chromosomes, happens randomly throughout the chromosome, then you can see that the odds of that recombination happening between A and B are much smaller than the odds of it happening between B and C. The reason is because the distance between B and C is much further apart, and so that random chance can happen much more easily in this large section than it can between these tightly linked genes here, A and B. So this information allows us to do recombination mapping. And so we'll get into the calculations in a second, but based on this, we can glean a map of a chromosome. So there's some kind of general rules in that these distances are generally additive. And so if we were to look at just 2 genes, we could see, okay, the recombination between A and B is 5 map units. That's this recombination distance. It can be called recombination distance or centimorgans or map units. It has a bunch of different names. So if you hear centimorgan or map unit, generally the same thing. So we look at individuals that have come from a mating, and we see that a certain percentage leads to a map distance of 5 between A and B. And we then look at the recombinations between genes A and C, like we had down here at the bottom, And we see that that distance is only 3 map units. So gleaning this information, we have two possible outcomes because they're additive if they're on the same chromosome. Either A could be in between C and B, and so we'd have that 3 map units from here, and we'd have that 5 map units from here, and we'd have a distance between C and B of 8 map units. Or we could have a conformation of A, C, B, where A and B are on the outside. I'm going to change the color here. Let's do purple. Where A and C are on the outside, or A and B are on the outside, excuse me, and that the distance between A and C was 3 map units. So that one comes down here. And that would result in the distance between C and B being 2 map units. So now we're going to go into how we actually calculate this. Actually, before we calculate this, I forgot I have one more slide here. So this is just showing what I drew in the last slide. So as you can see here, we have A, B, and C, again, these genes. And this slide is just showing, again, the idea that if there's a greater distance between genes, there's more likely to be crossover events between them than if they're very close together. So we have here 4 offspring, myocyte 1, 2, 3, and 4. And as you can see, in the first one, we have crossovers between B and C, and that's it. The second one, we have crossovers between B and C, that's it. The third one, we have crossovers between B and C, that's it. And then the fourth one, we have crossovers between A and B. So because in our population, there's more crossovers between B and C, we know that they are farther apart than A and B, which had a much rarer occurrence of crossovers between those two genes. Okay, so for this map distance, we have to have a trihybrid cross, right? Because A, B, and C, we had 3 genes. So in this example here, we're going to calculate the distance between genes. So in parent 1, we have the wild type V plus V plus, and then CV and CT that are homozygous. And then in the other individual, we have the opposite, the reciprocal, right? So we have VV, then CV plus CV plus, and CT plus CT plus. So our gametes are V plus CV CT, and V CV plus CT plus. So when they come together, these two gametes, we are heterozygote for all 3 genes, right? Then we do a test cross to the recessive individual. So we have the recessive being VV, CV, CV, CT, CT. And so from this information, we would assume that there are 8 possible gametes, right? So you have, from the offspring, you can either be V or V plus, so that's 2, times CV or CV plus, so 2, times CT or CT plus, 2. So we have 8 possible combinations. So those 8 possible combinations we can put in this table. And so here we have one combination, V, CV plus, CT plus, V plus, CV, CT, V, CV, CT plus, V plus, CV plus, CT, etc. I'm not going to name them all. And so those are 8 possible combinations of those genes from those parents. And so in a test question, I'll give you this table, but not with the R's. I'll get to the R's in a second. But you'll have generally this information right here given to you. So now if we look at our table, we know which ones are the parental generation, right? Or the parental generation are least likely to have recombinants because recombination is rare. So we can see that this and this are what our 2 parents were, right? And if you go back to the last slide, you will see that that was 2 of our parents' gametes. Now from there, we have to identify which individuals are the recombinants. So looking at this first individual here, we see V plus, or V, CV, and CT plus. Now, our recombination can either happen between V and CV, V and CT, or CV and CT. So we put those across the top, and that information will be given to you as well. So what we do is we compare, I'm not changing my color here, we compare this individual to the two parents. And so we see V and CV, our first comparison, does not happen in any of the parents, right? We only have V plus and CV, or V and CV plus. So the combination of V and CV together is not in the parents, and therefore we put an R here for it being a recombination event. We go down to the next line and we compare this individual, V plus and CV plus. Looking at the parents, we see that a plus on the V and a plus on the CV does not occur. So this too has to have been the result of a recombination. We move down again and we see V times CV. Again, we already did that up here. Again, that individual has to be the result of a recombination because it's not in that parent generation. And then V plus CV plus is not in the parental generation, and thus is a recombinant. We get down to this fifth line and we have V CV plus. One of our parents had V and CV plus, so therefore it's not a recombinant. And then the last line, V plus CV, is also one of the two parents and therefore not a recombinant. So next we move over to the next combination. So I'll change my color. Let's do light blue. All right, so we have V and CT. So we do the exact same thing. So V and CT, we have V that is mutant and CT plus, that is our wild type. And we see that that is the same as this parent. And so that means that it is not a recombinant. We move down a line and we have V plus CV plus, or sorry, V plus CT, because we're doing the second line right here. So V plus and CT is in one of the parents. So therefore it is not a recombinant either. We move down another line here and we do V and CT, and we notice that there is no V and CT in either of those parents. Therefore, this is a recombinant. Move down another line, V plus CT plus. That does not occur in one of our two parents. Therefore, this is a recombinant. We move down again, V and CT, not in the parents, recombinant. And then lastly, V plus CT plus is not in the parents, and that is a recombinant. And so lastly, we're going to go over to CV and CT and do the same thing. So that's these last two genes. So we have CV and CT plus, not in the parent, therefore it's recombinant. We have CV plus and CT, not a parent, again, therefore recombinant. We have CV-CT, that is a parent, so it's not recombinant. Make sure I'm on the right line here. CT plus and CV plus is a parent, not a recombinant. And then we have CV plus CT, recombinant, and CV plus CT plus, not in the parents, recombinant. So there are some tricks or like fact or checking yourself that you can do. In these 3-point test cross, there will always be 4 per column. So if you have less than 4 or more than 4, you've messed up. And there will always be 2 per row. Besides that, ignore the parent part, but there will always be 2 per row, right? So here we have 2, here we have 2, here we have 2, and there'll be no more, no less. So that's an easy way to go back and check to make sure that your table's set up correctly. Okay, so from this now, at the bottom, we're going to count these or add the numbers in our columns with R. So if we add up 45, 40, 89, and 94, we are going to get, yellow is probably not going to show up so good. I'll just do black. We're going to get 268 here. Next, we'll go over and do the same thing and add the recombinant numbers from the rows with the R. So 89, 94, 3, and 5. And that gives us this 191. And then lastly, we're going to add up our recombinants from our CVCT row. So we have 45, 40, 3, and 5. And that gives us 93. So from this information, we can enter this formula to determine the recombination frequency, or the likelihood of recombination between these genes. So first, we're going to do V and CV. So we take our number of recombinants and we divide it by our total number of individuals, which is right here, and we get 18.5% recombination frequency. It's how often out of our population there was a recombination between V and C. Next, we do it again with V and CT. So we take this 191 and we divide it by our total number, and we get a 13.2% chance of recombination happening between V and CT. And then lastly, we do it with the difference between CV and CT. And from that, we do 93 divided by our total number again, and we get a 6.4% chance of recombination occurring between CV and CT. And one thing to take into account is, because there is less than 50% recombination frequency, we assume that these three genes are on the same chromosome. If you get a recombination frequency at 50 or above, that means that the genes are not linked and that they are on different chromosomes. Because if your chance is 50-50 of getting a gene, say for instance getting CV plus and V, if it's 50%, that means that that ratio came from your 50-50 shot of getting your mom's chromosome or your dad's chromosome. So if these numbers are below 50%, they are linked. If any of these numbers are above 50 or above, or around 50, then it is not a linked gene. Okay, so let's try to put these genes on a map. So remember, we had between V and CV, well, those probably shouldn't be so close together, we had 18.5. Oh yeah, that's bad. All right, 18.5. Between V and CT, we had 13.2. And then between CT and CV, we had 6.4. So we know that they're on the same chromosome because our recombination is much less than 50%. So if we put these together on a map and say our distance between V and CT is 13.2, and then we knew our distance between CT and CV was 6.4, our math doesn't add up, right? Because we predicted that the distance between V and CV would be 18.5. But if we add these two numbers together, and we remember we had that slide that said that things were additive, we get 19.6. So why is that? So the reason for that is that we're not counting double recombinants. So in the comparison of V and CV, it's possible that we get recombination between where we swap out the middle gene, but we leave V and CV alone. right? So we get this double recombination event that happens in between two. So if we were looking at, for example, this comparison between V and CV plus, it would look like it is a parental genotype, but CT's been replaced, so it's not. So it is a recombinant. And so we're ignoring that in our math, and that is affecting our calculation. So if we wanted to get our math to work out correctly, we could relook at this table. And so we see that these two individuals, where we have our smallest portions, 3 and 5, are double recombinants because it's really rare compared to our parents that had, or parent genotypes that had no recombination. And so what we would do then is say, okay, this actually between V and CV does have recombination occurring, but it just happens twice, right? So from there, we would add up everything, and we'd add this column twice, and we'd get 45 and 40, 89, 94, 3, 3, 5, 5, and we'd get 284 total individuals. And we do the math, and that's how we end up with that 19.6. Now, this is just kind of a step for checking your work, so to speak. But generally, simply adding the smaller two values gives us that good estimate. And so you don't have to go through this. You can always just take the information that adding those two small values will give you the distance between the biggest value. So in our example where we had, we came up with 18.5, that would give us the information that C, V, and V were on the outside, and that the other two distances in between would give us the information as to who is, or the overall distance, right? So adding the 6.4 and 13.5 or whatever it was would give us our correct distance on the outside. So this step, while it does kind of give you kind of a fact checking or double checking your work, you can also just get away with adding the two smaller values together to get the overall distance of the large, the two outside genes. And so one thing to keep in mind when doing this is the order of the parental genes can all be different. It's not always where we're going to have V, CT, CV, and then V plus, CT plus, and CV plus, right? So the parental genotypes can lead to, these are all different recombinants with the genes all shuffled up. So pay attention to that largest value, because that's going to tell you who is the parental genotypes. Don't get into the habit of thinking, okay, one parent's going to have all mutants and one's going to have all wild type, because it can be a mixture. Okay, so one more calculation. Believe me, this is, once we get through these, the calculations are generally over. But we need to do chi-square tests for linkage. And so if we have a population where we infer that two genes are linked and recombination is less than 50%, we need to do statistics to make sure, because some of those numbers are sloppy, right? Like we look at the, the ratios, and that kind of looks like 1 to 1 to 1 to 1, but we have to make sure that these alleles are segregating properly. And so because we don't know the distance between genes, we can't predict ratios and test for linkage. But because we have these Mendelian ratios, we can test for the absence of linkage. So we can test to see if they're not linked, and that will tell us kind of if they are linked or not. That's kind of our null hypothesis. So in this case, here's our individuals. We have 500 total offspring, and this is just a dihybrid cross, or a dihybrid test cross, right? And so we have individuals that have big A, big B, we have 142. Individuals that are little a, little b, the other parental genotype over here, we have 133. Big A, little b, we have 113, and then big A, little b, we have 112. So remember, in this test cross, because this is a test cross, we're assuming with independent assortment that we have a 1-to-1 to 1-to-1 ratio. So what we can do from that is we can set up this table, and we can look at the segregation of those alleles individually. And so what we have on the top is big A and little a. And on the side, we have big B and little b. So that's, this and this right here. And so if for the individuals that have a big A here and a big B, we put that number into the table. Individuals that have a big B and a little a, which would be big B, little a, 112, we put that into the table. Individuals that have a big A, little b, which we see right here, we put into the table. And then individuals that have a, little b, which is this one, we put into our table. So now we're looking at the segregation patterns of these. And so the segregation of big A and little a is this column. So we have 255. The segregation, of big A and one of the B's. The segregation of little a and one of the B's is 245. And then conversely, in the rows, we have the segregation of the B from the A's, 254, and the segregation of little b from the A's, 246. Okay, so I just took this from the last slide, just move the table over to give us more space. And so now we can find our expected values for chi-square using these allelic proportions that we made. So our expected number of A, B, or individuals that have big A, big B is our big A row or column, so 255, and our big B row, 254. So we take our big A and make that into a proportion, so 255 out of 500. And we take our proportion for big B, 254 out of 500, and then we multiply that times our total population, and we would expect, giving everything being equal in Mendelian ratio, that we'd have 129.54 individuals that would have a big A and a big B. Next, we do it for big A, little b. So we take the big A row again, 255. We take the little b row, which is 246 over here. We enter that into our equation, 255 and 246, times it by our whole population, and we end up with 125.46. And we continue to do that for our last two, little a, big B, and little a, little b, and we get our expected values down here. And now we can find chi-square values. So in this table here, we have our big A, big B combination, and we have our observed ratio, which is what we saw in this population. So we had 142 individuals that were big A, big B. And our expected, though, is 129.54, which we calculated right here. And so the chi-square formula, this should actually not be, this should be raised to the 2, so it's squared, is observed minus expected squared divided by expected. And from that, we get 1.19. Now we move down and we do it again with little a, little b. So our little a, little b was 133 here. And so that was our observed. Our expected was 120.56. So we enter that into this equation, and we get 129. So we do that, or this is 1.29. So we do that for all four of these, and we add up our total chi-square value, which we end up with 4.97. So now we have to calculate the degrees of freedom for chi-square. And normally degrees of freedom, if you take in stats, is the number of observations or values minus 1 and minus 1. But however, because of these, the values in this table are all dependent on each other, and so A is counted on multiple rows and B is counted on multiple rows, etc., we actually treat it differently. So degrees of freedom is actually the number of columns times the number of rows. And so in our case, it's the number of columns minus 1 times the number of rows minus 1. So in our case, we have 2 columns minus 1 times 2 rows minus 1, which gives us 1 degree of freedom. So now lastly, we are going to look in the chi-square table here to see if these genes are assorting independently or if they are linked. And so from this, we have our chi-square value of 4.97 with 1 degree of freedom, so this top row. And we take this value of 0.05 as our confidence interval. And so from this information, 4.97 falls on this side of the our critical value. So because our hypothesis were that the genes were on separate chromosomes, which would be part of the Mendelian ratio, remember it requires independent assortment, this p-value is larger than our threshold of 0.05, right? It's to this side of it. Therefore, we must reject the hypothesis that there is no linkage and infer that these loci are indeed linked, right? So because we're assuming that everything assorted Mendelian, and because our value was higher than our 0.05 thresholds to this side, we say these are not assorting Mendelian, and that instead there is linkage between these genes. And so that's how we do the chi-square test for this.